Welcome everyone to today's webinar. My name is Dan Combest, and today my colleague Paolo Jeremia is actually going to be speaking. And today's topic is HELYX and ELEMENTS version 3.3 release highlights. First off, we're going to introduce ENGYS and some of our CAE innovations. So that's kind of the overall webinar goal that we always have. But this is more focused towards what's coming out in the new versions of HELYX and ELEMENTS. And like I said, several of these topics have been introduced in past webinars. And then there's also a few upcoming webinars that will actually dive a little deeper into these different topics. As always, we'll answer all these questions at the end, and we'll continue via email post-webinar. And if you'd like to ask a question via email, all you need to do is reply to the invitation to the webinar, and it will go directly to me. And either I'll answer or I will have Paolo or one of my other colleagues answer and clarify your question. Before we dive into it, I want to talk about the ENGYS user group meeting. So we have this scheduled for September of 2021. It's going to take place in Detroit, Michigan. If everything is back on track with the world, then we will have this event. You can register at ugm.engys.com. For more details, we'll have an agenda that will be forming over the year and different topics. It should be training. It should be a day of training on elements and HELYX. It should be a day of presentations. There should be time to network with other users and talk about their experience. So it should be a great event. This is the third user group meeting that we've had, and both of the other ones have occurred in London, but this is the first one in North America. Just a little bit about ENGYS. We are global providers of CFD products and services. We were founded in the United Kingdom in 2009, and we're finishing our 10th year of business. We've always been focused on enabling open source software in industry, specifically around the foam, open foam library. And I say foam because that was the open foam library before it was actually open source. So we have people within the ENGYS organization that have had experience with this library since as early as 1999. We actually have 8 offices worldwide: the UK, Germany, Italy, Greece, here in the US, Australia, South Africa, and Brazil. And we have an established distributor network around the world in Japan, South Korea, here in the US, France, and Spain. Just a little bit of information about our products. There's 4 main groups. The first is HELYX. This is a general purpose open source CFD software. This includes meshing, problem setup, simulation, and post-processing. Elements is an advanced open source CFD software specifically aimed at the automotive world. So I would describe it as a superset of HELYX, but with other tools like an external aerodynamics wizard, more focused application towards underhood thermal, coupling with other tools that would enable more detailed underhood thermal simulation. The next group are HELYX add-ons, so adjoint optimization, block-coupled solver. Paolo will be talking a little bit about improvements of block-coupled solvers, marine hydrodynamic solvers, and advanced multi-phase flow solvers. And then finally, we have HELYX OS, which is an open source GUI for standard open foam. All right, so with that, let me stop sharing and then let me pass this off to my colleague.
Okay. Thank you, Dan, for the introduction. I'm Paolo Jeremia and I work for ENGYS in Italy, and today I'm going to talk about release highlights of HELYX and ELEMENTS version 3.3. Here is the agenda for today's presentation. So let's start from a brief introduction to the main features available in 3.3, and then I move into Generalized Internal Boundaries and talk about the new addition in the mesh component, in the setup, new solvers, new features in the view tab, and then I move into the new HPC interface that we made available for both HELYX and ELEMENTS, and finally a few words about the external Aero wizard available in ELEMENTS. What's new in HELYX 3.3? Well, first of all, let's just mention generalized internal boundaries, which I'm going to talk about later. This is one of the main features that we made available to this new version. Then we add new functionalities, a new measure available in mesh component, new features in the setup panel, new solvers, which I'm going to talk about later, new features in the view tab for the visualization part, and finally new run mode options and presets for HPC. So all these features are made available at both core and GUI level. And in terms of Elements 3.3, what's new? Well, in Elements you have all the options and all the features you have in ELEMENTS, plus some additional components which are designed for the automotive industry, like my colleague Daniel mentioned before. So we have the same GUI and core components as HELYX 3.3, but in addition to that, we have new features. So for example, in the context of external Aero, we have a new workflow for accurate wheel modeling using generalized reference frame approach, which is a brand new methodology that we have developed in ENGYS, and I'm going to talk about this later. Then we have new reporting capabilities with a new layout and new options for the report in order to publish our results when you get a simulation done. And finally, enhanced visualization for large cases, which is really needed for external aerodynamics. Moving to the main functionalities of the software, well, first we have Generalized Internal Boundaries, GIB, which is a new methodology available in a finite volume that we developed inside ENGYS, which is designed for complex motions and conditional internal boundaries. If you are not familiar with this, if you want to find out more, there's a nice webinar that my colleague Daniel held a month ago. You can find more details in our website. There is also a recording, so if you want to check out, there is also a list of application cases and the background for the underlying theory behind this method. But in short, this method is you have this background mesh. In this very simple case, you have a background mesh with a snapping surface, okay? And in this particular case, we have a cylinder which moves in a oscillated linear motion fashion. And this snapping basically creates two faces, a pair of faces, a master and a slave, which are external and internal. And this is basically where you apply this internal boundary condition. The beauty of this is that you can define this boundary condition in an exact way. So you can add the exact contribution to the matrix, same as the body-fitted grids, but with the even advantages of the internal boundaries in terms of robustness and flexibility. So this works now for single phase and VUF solvers. We have full support in the GUI. And in terms of boundary types, we have static and dynamic walls. Like in this case, we have a dynamic wall moving up and down. Invisible surfaces, which are basically a pass-through type, and then inactive. Looking at the complex motion, what we can do is rigid body motion or 6DOF. Like in this case, we have a lifeboat and a VF solver, so you can see the action motion of a body in all the forces considered here in the context of a VUF simulation, multi-phase simulation. How do you create GIB? Well, you can define the GIB via an external geometry provided in STL format or using an internal phase inside the mesh. In addition to complex motion, we also have GIB for conditional boundaries. So, for example, we have in this particular case, we have in this animation an example of fuel sloshing trapdoor. So you can see here there are some openings. There are some doors here that behaves like an opening or a wall, depending on some specific options. So you can have, for example, as a criterion, the pressure difference between the two sides or velocity falling below a specific threshold value and things like that. And this is what we call two-ways GIB, so on and off, so on and off with respect to the opening and wall. And then you can have also one way, which is for example, a breaking window. So a wall becomes an opening, and there is no way to return back to a previous state. If you want to return back to a previous state, you might want to use the time varying on-off option. So you have a tabulated GIB as a function on time, and this can be used, for example, to simulate a door opening and closing inside a train or a building, for example. Time varying on-off tabulated GIB can be extended and used to perform things like design variation and design permutation, such as parametric studies and DOEs. In terms of mesh, let me just mention the new algorithm that we have developed for 3.3, which is called the Extrude Mesh algorithm. We have new option for the volume and surface refinement inside the castellated switches, and new options for the dual mesher algorithm, which was made available a few years ago to enhance the quality of the near wall layers. Then improved robustness and performance, and new mesh tools and related interface. In terms of the extrude mesh algorithm, it's a hybrid method for the meshing that we made available in 3.3 for layer addition. So as you can see here from this picture, this combines the benefits of the standard mesher with the benefits of the dual mesh. So the standard mesher, it was really good in the far field in terms of robustness, whereas the dual mesh is very efficient in the near wall region, the boundary layer. If you combine the two methods, this is what you get. So you get a nice boundary layer with the far field smoothness and transition like you can get in the standard mesher. And this is what we call extrude mesher. The result is a high quality mesh generation tool. We have other mesh enhancements, like, for example, a new mesh statistic panel where you can visualize statistics in terms of cell types, a number of cells, volumes, area, surfaces, normals, and so on. And you can also create cell zones now using primitive shape, STL. You can create a GRF that I'm going to talk about later using automated method called swept patch approach. And finally, we can visualize surface normals for both geometry and mesh surfaces. It's very important, for example, for zero thickness surfaces to see which side is which in order to apply the correct boundary conditions and mesh properties. In terms of setup, we have new turbulence models, a new interface for our newly developed GRF method, new boundary condition, and a new thermal comfort index interface. Regarding turbulence model, let me just mention this new liquid blending lag K epsilon turbulent model, which is now available in 3.3. It's a Reynolds stress model derived, so it's very accurate when it comes to capture the wake vortices in the strong separation areas, for example, behind a car in the context of external aerodynamics. Just think about areas like the A-pillar vortex, where you have strong curvature. It's very difficult with the standard traditional runs models to detect this. This one performs quite well, and it brings improved accuracy as a result. We do support this in the GUI, so it's fully supported. And you can run this with both low Reynolds and high Reynolds meshes, so we have adaptive wall function for this. And also we have a rough wall function in case you want to account for roughness. And finally, we improved the low Reynolds wall function, which were previously made available in the previous version of HELYX with a new implementation. In terms of boundary conditions, we have new addition mainly in the GUI. For example, we have an interface for a time varied point data boundary condition, which is basically a boundary condition which interpolates fields from a tabulated map of values as a function of time and space. So for example, here we have a velocity applied at the inlet, which can be read from a tabulated ASCII file, where you have the position in X, Y, and Z, and the corresponding values of velocity. And this is at a prescribed time, but you can have also a function of time. So you can have multiple matrices here, multiple tables. And this interpolation table is supported for momentum, velocity, and pressure, for thermal and phase fraction fields. And of course, we have interface for Excel and CSV import format. In terms of thermal boundary condition, we have a thermal coupling boundary condition to enable two-way coupling to third-party thermal solver. For example, we have an interface to Thytherm from Thermoanalytics, and this is supported for both steady state and transient thermal loading cases. We also have a new mass flux concentration boundary condition for CO2 smoke and humidity at walls, in addition to the existing options available for walls for these scalars. And finally, we have a new roughness wall function interface and implementation, which was completely refactored with respect to the previous version. In terms of thermal comfort, we refactor the existing thermal comfort tool. So we now accommodate new comfort metrics based on different rules and different ISO and standards, ASHRAE and so on. So we can calculate PMV, PPD, sets, PHS, and so on using the new implementation made available at core level, and also thanks to the help of a graphical user interface, you can easily assign these quantities and assign the sensible defaults, like you can see here in this image. In terms of solvers, we developed new solvers mainly in the HELYX coupled add-on module. So these solvers were developed by ENGYS and are basically represent a major update with respect to the previous version. So for example, we have a pressure-based block coupled solver for incompressible flows and a density-based block coupled solver for compressible flows. The way it was done, it was basically a new block matrix framework, which was rewritten from scratch with respect to 3.2, with the objective to have a full compatibility with the subsystems and components available in the standard HELYX. So this means you can exploit all the boundary condition, physical models, turbulence model, and so on that are available in the segregated solver. And this wasn't the case in the previous version of HELYX, where we had some special solvers for the HELYX coupled add-on. So in this case, the compatibility is 100%. Well, it's not only that; it's also the improvement in terms of results we achieved that I want to talk about today. So, for example, let's have a look at the incompressible flow solver, the incompressible coupled solver. And let's have a look at this case. We have a centrifugal pump with 6 in parallel braids, 2900 RPM, and we have 5 operating points with 5 flow rates. This mesh was created with using the Extrude algorithm. It's about 11 million cells, and we run using a steady state MRF k-omega SST model. This is a standard approach for this kind of problems. And what we would like to do is to compare the results to segregated and HELYX 3.2 incompressible coupled solver. So this is what we have in terms of characteristics. So we have the head, the coupling power, and the efficiency, and the leakage to account for the mechanical losses. And you can see there is a good agreement between the different methods, as you might expect. But what really matters here is this slide. So you can see here the convergence time. So on the top, we have the segregated CPU time in terms of hours. This was run on 32 cores. And you can see the CPU time for each operating point. This is the segregated. On the blue line here is the couple solver in the 3.3 version, whereas the black line here is the couple solver in the previous version of HELYX. So you can see there is a 60% consistent speed up between the couple solver in the new version of HELYX versus the segregated one, but also a 20% reduction in solution speed versus the couple solver available in the previous version. So things were improved in this regard. Not only that, we also improved in terms of memory footprint. So we measured an average value of 30% reduction in memory footprint with respect to the previous version of the couple solver. So in terms of visualization, we have new features for rendering, improved case loading, a new runtime visualization component, a new way to animate scenes, and a new threshold object. So you can see here, this is all done inside the View tab. Well, in terms of software rendering, we improved the way the algorithm work. So both HELYX and Elements have client-server architecture. So you have your front end, which is called HELYX client, which communicates with the server via an SSH tunnel, and the server can run also on HPC, so you can distribute the visualization, the rendering on multiple nodes, same as you do for computation of a solution of your solver, of a mesh, or a generic application. And then once each node finalizes the rendering process, the image is composed and retrieved and sent back to the HELYX client via an image compression algorithm, again using an SSH tunnel. So you can interact with the display and repeat this process, this loop, for every action you make. What we did was to improve the memory handling for large cases in case of HPC, to enhance stability for high latency connections. So, for example, if the SSH tunnel goes over the internet, we made the interaction faster than the selection of objects in the 3D viewport much faster, especially for geometry cases, and we support multiple computational nodes, for example, using InfiniBand. If you don't want to do software rendering, you can do OpenGL rendering, and in the new version, we now let the user choose from standard to high performance OpenGL backend. So we have a new implementation, and high performance OpenGL is usually supported by modern graphic cards, but we leave the standard as default for legacy system. So let me show you an example here. So if you have a single surface STL 1.3 gigabytes and you want to see how the rendering performs using the two backends. So for example, in this particular case, we want to switch from surface representation type to wireframe representation type, which is more demanding. So this is the standard. On the top, on the bottom, we have the high performance, and you can see here that now you switch at some point here. Okay, you can see that is in the bottom side is almost immediate, whereas here is still doing something. Okay, now it's ready, but you can see it's much slower than the second one. So this is by far the recommended setup in case you want to do the rendering on a GPU. In terms of case loading and STL loading, we have a new STL reader which runs 40% time faster than the previous version of HELYX. So for example, if you look at the same STL, if you want to see just the loading time in 3.2.1 and compared to 3.3, this is what we get. So 3.2.1 on the top, 3.3 on the bottom. And you can see the progress here. You can see that in the bottoms case in 3.3 is almost done, it's done now, and whereas in the 3.2.1 is still loading, and there is a bit of delay. So So we measure about 30% improvement in loading time. We have a new multi-region ENGYS binary format, so loading time 40% faster, and new selective case loading, so users can decide what to load at startup. So any combination of the following is allowed, so surface or volume mesh or geometry or even nothing. So this is very important, especially for large cases and to speed up things. You can create animations now. You can animate flow values on the fly, for example, using the runtime visualization library. So you can create images on the fly, or you can use the save to image to create images afterwards once the simulation is done from the available time steps. How do you do that? You select the scenes, what we call scenes, inside HELYX view tab to create images. And in terms of HPC interface, we have a new interface for Slurm, batch scheduling system, with a factor of around mode to make it easier to customize. We added enhanced portability of around mode. We have new MPI built options. This is because we upgraded our MPI to a newer version in our core. And we have a new interface for HELYX On Demand HPC via Ceros from the EPCC. So this is the interface for Slurm, which is very, popular among the engineering community, and we added to the list of available queue systems. So you can add your own scheduler parameters here using the GUI. In terms of elements additions, let me just mention the new wheel treatment via the GRF. GRF is a new, stands for Generalized Internal Frame. And again, if you're interested in this, there is a webinar that my colleague Daniel held last week. So just find out more on our website to check out the recording and more details. But in short, this is a tool which creates a multi-reference frame for deform and scan tires by applying a rotating frame in the grooves, in the transverse grooves in the threads, where the standard multi-reference frame MRF approach fails. So this is applicable to any shape, even non-circular, such as a scan tire with deformation applied. And what it does, it creates these cell zones where it applies this momentum source, like in the areas highlighted in green here. And this is usually coupled to sliding mesh approach applied to rims to provide very accurate solutions. So how does it work in Elements? Well, first you set up the GRF in external Aero wizards. There is a specific interface in the wheels panel to enable the GRF and to compute the axis and the center of rotation of the wheel. And this can be automated using templates, of course. Then you create the mesh, you get these cell zones created, and finally you run the case. And this is what you have, this is what you have for a transient solution with sliding mesh and moving rotating hub, you can see. Then we have a new report tool with bin and drag and lift development charts, a new layout and format, enhanced flexibility, and we also improved on the memory handling for large cases. Okay, so in conclusion, HELYX and ELEMENTS 3.3 will be released in October 2020. We have more than 100 new features and extensions with respect to the previous 3.2 versions. We have an ambitious long-term development plan and goals leading to what we call internally version 4. And we would like to put special emphasis on extended multi-physics and modeling capabilities. This is our target, and we are developing brand new solvers for that. Of course, your feedback and our clients and users' feedback is very important for us, and it shapes our development strategy. So I think that's it for today.
Hello, thanks. Appreciate that. That was really good. It's a lot of things to fit into that 30-minute-ish window, so appreciate that. Let's see, we have a few questions. let me see the first question. Does the Python API drive runtime visualization? So can you use the Python API to drive that process?
Yeah, what we usually do, we use our Python API via the journalist. So you record a macro to define a series of scenes with specific views and camera settings and so on. So if you want to have a slice or a streamline, you just record this. And then you can populate your configuration file, which is written inside the case. Then, once you are done, you go from the command line and you run this in batch mode, and this is how you get these images generated at the runtime.
Gotcha. And I know that, you know, it's written in Python, so you're able to turn things into functions, pass variables to these functions that drive case creation and embed loops to loop through things. So you can adjust a journal to kind of extend the capability.
Absolutely. If you are familiar with Python, it's very flexible, and you can take advantage of the Python functionalities and extend to the libraries available in Python and all the packages.
Gotcha. Yeah, absolutely. In terms of runtime visualization, what is the performance hit per iteration or per, I'm guessing, when you output an image?
Okay. The answer is it depends on which kind of image you are creating. So if you are creating something on the internal volume mesh, this takes a little bit more to load a surface mesh or a geometry. So based on our tests, it varies from 10 to 20% overhead. Yeah.
And I do know that the kind of depth or the number of images isn't necessarily, it's not linear times 20%, because a lot of the overhead would be at least loading that first bit of data, and then afterwards making each image is actually not as costly if you already have something loaded for each time step.
Exactly.
That's my understanding. Yeah.
Exactly.
Okay.
It's the loading of a data set which is time consuming. Once it's done and in memory, then you can create as many images as you want with no extra cost.
Gotcha. Okay, perfect. One question: does the coupled solver for compressible flow work for CHT cases? So I can handle a little bit, and then Pablo might be able to answer this one too. But HELYX CHT, that is a region coupling approach, and at least for enthalpy, that is a coupled matrix across different boundaries within regions. At least the coupled solver that we're talking about here, it's coupled in terms of the momentum direction, so X, Y, and Z, and then pressure. And so it's coupled in terms of that equation, not necessarily multi-region. I think in the future, maybe the coupled momentum component of that could be included into CHT or HELYX CHT, but for now they're kind of separate. So HELYX CHT is not part of the coupled module. It's still part of the standard set of solvers that you can still use. And Paolo, I don't know if you have any other comments on this for this.
No, I think you answered the question, Dan. Yes.
Okay, gotcha. And if this didn't answer your question, then feel free to drop an email, or you can just drop another question while we're answering things here. Let's see. One other question talking about coupled solvers is, what's the source of the coupled solver speed increase between versions? From my understanding, the real difference is there's improvements in the algorithm from the 3.2 kind of code base of coupled up to 3.3. So there's improvements in the algorithm. There's also memory management improvements. So there's less mishits. So it's more efficient with its memory management. And then the last one was the linear system solver improvements in terms of the multi-grid solver that comes with it. So from my understanding, that is the major area of improvement, which actually gave that 20% improvement from the last one. Paulo, was it 20 or was it 40? I think you said 20%.
Yeah. It's on there. In that specific case, about 25%, if I'm not mistaken.
Yeah. Okay, gotcha. All right, I think that's it with the questions. If there are no other questions, or if anyone thinks of anything after the webinar, please feel free to hit reply on that email. Or if you're already a customer, you can send an email to our support email, and we will definitely get back to you. And appreciate everyone showing up today, and hope to see you at the next webinar. Thanks again. Thanks, Paulo.
Thank you.